Hello everybody, and welcome to video number 5 in this development vlog series of this game, Jerboa Wars, that we are working on. Today we are going to be talking about a serious bottleneck related to data transfer between WebAssembly layer and JavaScript layer. As you know, we need to update our scene on every frame, and that involves potentially a lot of data being pushed to the JavaScript layer from WebAssembly for every object on the screen that needs to move, rotate, scale, or any property change that need to be communicated to Pixie.js from WASM. It involves pushing that data through JavaScript interface. But before we look at the issue and the solution, I want to show you the example of what I'm talking about. All right, so this is another test that I wrote specifically to illustrate this issue here and the solution. As you can see, we have these sprites that are moving on the screen. By the way, if you see any stuttering, that's actually due to the screen recording software, not the not any issues with the frame rate. This is already using the workaround for the JavaScript WASM to JavaScript data transfer. Now, all of the properties are updated on the WASM side for these sprites and then pushed over to JavaScript side for the Pixie.js to render the scene, and that happens every frame. Now, and you can see we have 300 sprites on the screen, moving, all being transformed. Now, if I switch off the fast JavaScript interrupt, going back to the normal one where it's just using the standard JavaScript serialized data transfer. See, look at what happens. As you can see, the scene stalls to a halt. It's actually 10 is the minimum we can show, but I think it's way below the 10 frames per second. Yeah, it's closer to maybe 3 or 4, something like that, 2 or 3. And in our presentation today, we will look at why this happens and what we need to do to make it run as fast and smooth as it should. All right, let's look at the issue and the solution. Actually, in one frame. The presentation is going to be pretty short today because there's not much that's going on here, but it's quite interesting, I think. All right, so the issue is we have the Pixie.js, which is JavaScript, running in the browser on the client side. Well, all of this runs on the client side, of course. The WebAssembly runs on the client side, but they are not running within the same kind of scope, I would say. And on the Pixie.js side, we say we have a scene, and then they say, for example, we have sprites, and then these sprites, they have properties like the X position, for example. And we have on the WebAssembly side, in our application, we have a corresponding abstraction for our JSprite that has a container property that is it has a reference to the sprite object on the JavaScript side. But there's a link between them where now we have the X property on our JSprite that will use the JavaScript interrupt on the reference object to push data to JavaScript sprite object referenced by this and get the data from sprite back into WASM. And the way it's done is through the standard JS interrupt, well, also wrapped by the SpawnDevs library, which is very nicely set up. And say, for example, if we have a getter property on our C# object on the WASM side, we just call into ref to get this object, and it goes through JS interrupt layer, but it goes through this JSON serializer, where it takes the object on the JavaScript side, which is naturally JSON serialized, I would say, and then deserializes it back into the C# object that we have here on the WASM side. And the same thing, if we are setting the value, it takes the value, serializes it into JSON, and pushes it over to JavaScript, through JavaScript interrupt to JavaScript side, where it sets the property on the referenced object. Pretty straightforward in principle, but under the hood, there's a lot of stuff that's going on. What we see here is that the Pixie.js side is fast. We know that. The library is fast. The JavaScript itself is not slow at all. And the way that the Pixie.js developers set everything up is very efficient. On the same thing, we have the WebAssembly that by definition is also pretty fast. It's native code running on the client side. So, however, as you've seen, while Pixie.js is capable of rendering 300 balloons no problem, and WebAssembly is handling 300 setting and getting properties, like managing the properties of 300 objects on the WebAssembly side, no issues. We see the frame rate just non-existent. And the bottleneck is here in our JSON serializer. That is what's slow. Not serializer itself per se, but the thing is that the amount of data that we need to push on every frame. Say, for example, if we have 300 sprites and we have even one property that we need to update from WebAssembly to JavaScript, push it over there. That means 300 objects serialized to JavaScript and then pushed over all once per frame, which is 60 frames per second. And it's just one property. And usually we don't send just one property. We set, position involves two properties, the scale involves two properties, the rotation another property. So if we say even 10 properties here on one object, and we have 300 objects, that is 3,000 properties. And then we do it 60 times per second, which means 300 times 60 is going to be what, like 18,000? So 18,000 objects need to be serialized each second to JSON in order for us to sustain a 60 frames per second frame rate. And that is not happening. So what do? Is there a better way? And yes, there is. Since the JSON serializes the problem, a tip, not serialized into JSON. That's how we get out of it. But how to do that? And this is how we're going to do this. Instead of having this pipeline, using this standard pipeline, we are going to do some manipulations on both ends, on the JavaScript side and on the WebAssembly side. And on the WebAssembly side, this is what we're going to do. First of all, for the getter for each property that we need to push over to JavaScript side, the getter, we are just memoizing it on the WebAssembly side, in the C#. It's not completely memoized here because we need to get the initial value from JavaScript, and that is done once. But then when it's done once, we have the private field of the same type as our property, get the value first, and then whenever we're getting the value, we're getting it from the memo, not from JavaScript. So immediately the getter, we eliminate the round trip to JavaScript through JS interrupt. But the setter, we need to push. When we set the property, there's no avoiding it. We need to push the data from WASM to JavaScript somehow. And this is how we do it. First of all, instead of doing it immediately, what we do, we collect all of the information about which properties and which objects have been set into a kind of a ledger, memoizing a list of all of the things that have been set. So for example, if we're setting the X value on the sprite, on sprite 1, X, we kind of memoizing that assignment, let's say, of the value to and which object receives the value. We're memoizing that, the object, the property, and the value. And we do it for all of these objects that we need to set on the JavaScript side. And we do it on the WASM side, and collecting this information, building this ledger for every frame. So as you know, we have the render method on JScene. So as we are setting all these properties, this ledger is filled up, and then once per frame, what we do, we take this list of all of these properties that are being set. And this is where we serialize it still, but not into JSON. We serialize it into a byte array. just normal array of bytes. And see all of this happening here on the WebAssembly side. We are not touching JavaScript yet. And once we have that, once per frame, once we have the byte array with all of the data about which properties, which objects, and which properties in which values we set, we take this byte array, and that is when we push this over to JavaScript side. And here's the trick here is that when we push byte array over, it's still JS interop is still involved, but we don't have JSON serialization. So the overhead here is in constructing the ledger, in serializing constructing the ledger, there's a little bit overhead there, but it's not much. Where the overhead is in serializing into byte array, the same ledger, and on this side, on the JavaScript side, when the byte array is received, is deserializing it back into JavaScript objects to setting all of these properties. So the overhead is there, but as you can see, the overhead is not in the JS interop side of things. The overhead is on the WASM side, and overhead is on the JavaScript side, and they are fast. And interestingly, the byte transfer, just byte array transfer from WASM to JavaScript is also extremely fast. It was actually much faster than I anticipated. I've been doing some testing, and I was able to get about like 10 megabytes of the byte array with 10 million elements transfer over to JavaScript, and still within the acceptable frame rate. Of course, we are not going to be pushing like none of the scenes, even with everything. If you have, like I said, if you have 18,000 assignments on the WASM side that you need to transfer over, it will. We do it pretty efficiently in our application. You will get maybe somewhere around maybe 100,000 elements or 100K data transfer for each frame, and it's only for those properties that are set. We're not transferring all of the properties all the time. So it works out. Even though there's overhead still involved, it works out just fine, and as if you've seen in the demo. So that's the gist of it, and that's kind of the simplified diagram of what's going on. And to be fair, it's not that complicated even under the hood. That's why we're not going to be looking at this video is going to be pretty. This video is going to be pretty short, but we will look at how that is done in our code. All right. Before we go into the Visual Studio, let's look at the basic architecture. Elements that we will be building and updating in our application, or in our JSON library, I should say. First, is we are going to have a short JavaScript module. As I said, there will be some JavaScript code in this project, but not a lot. And this is pretty much it. This is one library so far that is written specifically to accommodate this scenario of data transfer from WASM to JavaScript. And this, like most of it, all of it pretty much is related to deserializing the byte array into the properties of the JavaScript objects. And one method that is called from WASM to JavaScript is going to be this in this module that does the job of deserializing, accepting the byte array data and deserializing it back into JavaScript. So on the WASM side, what we'll have a class called the render shuttle, and that is the class that is responsible for keeping track of this ledger that I was talking about, the property setter ledger, and then serializing it into the byte array on the WASM side. And to integrate it into JSON, what we have, first of all, we have this render shuttle type property that we call property messenger, and that is that we're talking about. It keeps track of all of the properties that are being set on the WASM side to all of the scene objects, and once per frame serializes it into a byte array. JSON also exposes a method for this JSON for the scene objects to update the ledger, and that is called send property. So this is what we will be calling from our scene objects, and most of it will be in the base abstract class of JScene element. So it's not like we need to do this for every different type of objects that we're going to have in our scene. Most of it is done on the base class, so it's done once. And finally, we have this call through JS runtime, which is the JS interop, which actually calls into this JavaScript method, providing the byte array with all the property data as the single argument to that function. All right, and on the JScene element, which is our base class, as I was saying, for all of our objects like containers, sprites, and grid sprites, and everything else above that in all the instructions, we are just, for every property that we want to set the value on the JavaScript side, we have to, at some point, when the property is set, call the scene, which is a reference to the JScene object. We call the send property method, supplying information about which object it is, what property it is, and what is the value that we are setting. And that's about it. That's the whole architecture. And now let's jump into the Visual Studio and check out the code. All right, here we are in our project in Visual Studio. And today we're not going to be doing a lot of coding. It's all pretty straightforward, actually. We're just going to go through the files that I mentioned in the presentation and classes. So we have the pixie interop.js file, which is just a few functions in JavaScript that we will be, well, actually you'll only be calling one function from it pretty much. That takes the payload is this byte array and then updates all of the scene objects for all of the objects, for all of the properties that are set in this payload. It deserializes it and then sets the appropriate properties on the JavaScript side in Pixie.js. And you can look at it. It's very short. It's only about 120 lines of code. But to use this module, we need to first import it, I guess, in our component. And this is what we do. We're loading the script using the JavaScript interop from our JavaScript file. And this is what allows us to call that function to update the properties from WASM to JavaScript. That's all. Then on the JScene side of things, well, actually, let's look at the render shuttle itself. This class that I have here that is in charge of, as you can see, it implements a key collection of all of the properties that we want to set on the JavaScript side. And you can see the property assigner is a class that encodes the information about the target object, the property name, and the value. We have a collection of those, and as we are setting properties in WASM, we will be populating this collection, this ledger, and then the method, as it sets the property, it serializes it into a little buffer of bytes and adds it to the dictionary. And then we are just getting this data using the get data method. We're just taking the data and casting it as an array of bytes, because originally it's a list, of course, because we need to add stuff to it. But that's all there is. It just takes all of the properties that we set during our frame, and then once per frame gets a byte array out of them. And on our JScene object class, in our JScene class, we have this render shuttle object as a property. We call it the property messenger, just initializing, and as you can see here on the render frame, which runs once per frame, we get the data from the property messenger with all of the which gives us that byte array of all of the properties for this frame that have been set. And if we have any properties set, we call into JavaScript this JavaScript method that I was showing you in the module, giving the byte array as the single argument. And after that is done, we are clearing out our shuttle, our property messenger, because this operation is repeated every frame. So for this frame, it kind of like shuttles all of the property assignments and then starts collecting the properties to shuttle for the next frame immediately. All right, and on our JSON element, we have all of the properties. If you remember the way they were set up before, it was just directly getting the property from a container and setting the property on the container, which triggers the JSON serialization, all of that. So for every property, every time we set or get the property, it goes through the JavaScript interface, but not anymore. We're just going to look at one of them. So this is the property X again. This is what I was talking about, the memo of it. We have a private field X that is a nullable type of the same type as our property. And for the getter, the first time we are getting the value for X, we are actually looking at the X memo here. Actually, I have a flag here that I forgot to mention. Let me just quickly get back here. So I have the user byte array to shuttle properties property on the JSON object that is set to true, meaning it will use the property messenger to shuttle the property values. If it's set to false, it just defaults back to the old JSON serialization. This is how in my example you can see the performance of when we use the byte array serialization or we use the JSON serialization. Is just pretty much setting this to false for the old way and then setting it to true for the new way. And that is why here I have it as well. So if we have for the property on our object, we have the use byte array on the scene to shuttle properties on the scene set to true, then we are first looking at our memo value, and if it's null, then only then we are actually calling the getter from the container, which is calling it to JavaScript the old way. But as soon as the property is set, you will see later, then we are just going to be looking at this field when getting the property, as opposed to, we're not going to be diving into JavaScript layer at all to get the value for the property. But if it's not set to true, if we are using the old way, we're just going straight to the container all the time. For every time we call get, it will call into the reference object on the JavaScript side and do all of this JSON serialization and so on. But for the setting, what we do is a little bit more involved. Again, we are checking if we are using the new way versus the old way. And if we do, this is what we do. We are looking at the value property first. If the memo X is not equal to value, meaning, for example, if it's null or if it was something else, then only then we need to send the new value to JavaScript. Otherwise, there's no point. But if it's not, then we are sending the property with these arguments. This meaning the reference to the actual object that the property is that is the owner of the property. Then the JavaScript property name. As you can see, we have X as a capital X property on the WASM side, but on the JavaScript side, the property is lowercase x. So this is what we are setting on this object. We are setting on the JavaScript side the X, and we are supplying the value. And here we have to cast the little x because it is a nullable, and we need it nullable, and that's all there is. And that is the new way. But the old way, the same way we're checking if x is not equal to value, we are just setting both the memo and the JavaScript object property through the container reference to whatever the value is that we are setting to. So this is the fast way, and this is the old slow way, and all regulated by this use byte array to shuttle properties property, which is Boolean. And I have to repeat it for all properties that I want to set on the JavaScript side. There are not that many. There are about like 15 of them or something like that we need. At this point, we might add some properties later, but that's all we really need. I think that's about it. And let's look at the example once again. And actually, let's look at the code quickly of the example where I have my new page, which is the JS interrupt test. I have this little setup for this balloon thing, and here actually is not so much about the JavaScript interrupt side that I want to talk about, but about how I set up this scene with balloons, just to show you a simplified version of what we will be doing when we are building the next library, which is the JParts. And the idea is that we're going to be taking the JScene abstractions and then creating a more concrete kind of class, well, still abstractions for the objects that are closer related to our game, rather than just generic sprites and containers and all of that stuff. So this is the part where I created a couple of classes that extend on the JScene objects and other JScene classes to kind of make them more specialized than just sprites or containers. Like, for example, I have a balloon class here that inherits from JGridSprite, but it has all of the stuff here related to the functionality of a balloon. Like, for example, there's a method to move it up, and there's a method to wobble that updates certain properties on the object. And there are other things that going on. You can look at it. It's not that complicated. But the idea is that now we have a balloon which inherits from JSprite, which implements the iScene object interface, and we can directly add this to our containers on our scene. But at the same time, I have another class that I call the Festival, which is a collection of these balloons, and as you can see, it inherits from JContainer, which is also implementing the iScene object interface, which means I can just directly inject it into my scene. But here I have all of the functionality to, and it also, because it's a JContainer, it can accept other iScene object implementing classes, objects to its internal collection. And this is exactly what I'm doing. I am adding the balloons, which is the JGridSprite, to the Festival, which is a JContainer. And you can look at the at all of the methods that I have here. I have some options defining when I'm creating this festival, how many balloons I want, the minimum scale, size, like the scale variations, because the balloon sprite, as you will see here, has like 4 frames, and all of these things. But the idea is that if you look at this region festival, mostly like 3 classes that kind of encapsulate the entire scene for these balloons. I know it's simple, but it illustrates the approach to how we are going to build more complicated scenes with this, and kind of have this layered, vertically kind of integrated approach to architecture of our scene and our game and everything. So, and once we have that, as you can see, the rest of the page is very, very straightforward, and it does exactly the same things as we did before. We have our, where is it? We have our, the scene tester object, component rather, and it has the same events for the scene building and the scene initializer, which we're handling here. We have our single texture for our balloons, and we have the sprite grid from this texture created with these parameters. There are 4 frames, and this is what we will be using when we are initializing. And see, the initialization is very simple as well, because everything is encapsulated within the festival class. All we are doing, we are instantiating the festival we're supplying the parent as our scene render tree, and because it implements the JContainer, it will automatically add it to the render tree. We don't need to do anything else. And then we just call the method to make the festival, which accepts the argument, the festival options argument, which I only have here 3 things that I want to set up for now, which is the number of balloons, the speed at which balloons move, and the rate at which the balloons wobble. I have that set as constant fields here. As you can see, I have the balloon speed at 2, the wobble, all of that stuff. You can play with it. It will be pushed to the repository as usual, so you can clone it, download it, whatever, and run it for yourself and play with these properties and see what's what. But let's run this again and just check out the different scenarios. All right, so this is the 5th test that we have, fast JavaScript interop. And as you can see, actually, it randomly picks the colors, and it picked the frames, picked the green for all of them. Let me reload this just to have them. Okay, at least we have 2 different colors. Right. You can see the initial sprite count is 3, and we have the fast.js interop, which simply just sets that flag that I was talking about on JScene. And if I disable this flag now, you will not see any difference. And that is because the number of properties that we set is very limited. We only set the X and the Y for every sprite and send it over. And this is small enough number for the JS interop, the JSON serialized JavaScript interop to handle without dropping any frames. Now, but if I set this number to 30, for example, even, let me set the sprite count to 30, you can see that the fast JS interop is handling it just fine, no problem at all. Still, frame rate is very consistent. But if I switch it to slow method with the JSON serialization, you already see that the frames are already dropping for only just 30 sprites, which is nothing. Considering we will be having probably above 1,000 sprites at some point on the screen, considering all of the the particle systems and all of the tiles and everything. That is not feasible even for 30 sprites. To have the frame rate dropping to 20 is not great. But if I go further, as you've seen in the beginning of the video, if I set it to 300, once again, that is closer to the number of sprites I would like to handle in my game at any given time. With the fast JS interop, it works just fine, but with slow one, it's non-functional at all. But I'm glad we have this option. There is this method of transferring data between WASM and JavaScript without going through the JSON serialization. All we had to do is come up with our own way to serialize and just build it on a little bit lower level with the byte array. And after that, everything else works just fine. All right, I hope you find this maybe a little bit useful for whatever projects you're working on, and I'll see you all next time. Cheers.